Greetings professors, we are from Lab P4 Group 2 and our presentation is about Gen AI as a learning tool to conduct a comparative analysis of Dijkstra's algorithm and A-star search along with an interactive maze application. Our agenda begins with our objective, introduce both algorithms, outline our prompting strategy across multiple AI models, perform a technical comparative analysis, and conclude with a live application demonstration. Our goal is to use Gen AI to deeply understand and compare these two algorithms, visualize them in a maze application, and make learning interactive by having a player compete against the algorithm. At a high level, Dijkstra is a greedy breadth-first search algorithm for weighted graphs that operates without a defined goal, computing the shortest path from the source to all nodes. A-star extends Dijkstra by introducing a heuristic function, shifting it to a best first directed search. This heuristic penalizes nodes that deviate from the goal, making A-star significantly more targeted and efficient when a specific destination is known.
Hi, this is Yuan, and I'll be introducing why we chose to compare Dijkstra and A-search specifically. There are two main reasons. First, we wanted to evaluate how effective Gen AI actually is at explaining algorithmic concepts, particularly whether it can clearly identify the efficiency differences between two algorithms that are quite similar in structure, and whether it can break down A-specific concepts like optimality and consistency. Second, both algorithms have distinct real-world use cases, which makes them great candidates for practical learning, and that's something Gen AI should be able to enhance. Next slide, which is prompting strategy. So to ensure a fair comparison, we tested 4 AI chatbots: GPT 5.4, Gemini 3 Flash, Claude Sonnet 4.6, and DeepSeek 3.2. To keep things consistent, we used a standardized prompt template. This controls for behavior, formatting, and context across all models. And as you can see here, the template defines the role, task, evaluation criteria, and output format.
Let's begin the comparative analysis of Dijkstra and A-star search. We start with a deep dive of Dijkstra's algorithm. It has 3 main data structures, this two which contains the current shortest path from the start to every node in the graph. H2 stores every node's previous node, and backtracking this allows for path reconstruction. The priority queue stores all nodes and their distances, and the minimum H pair related to the explored node is chosen at each step. The main function of Dijkstra's algorithm is node relaxation, and for every neighbor of the current node, a new distance is calculated by calculating the distance to the current node and the distance to step over from the current node to the neighbor node. This is compared to the current distance of the neighbor, and the neighbor node is relaxed if a shorter distance is achieved. However, Dijkstra does not work with negative weights. This is because Dijkstra is a greedy algorithm, and the next shortest distance to an unvisited node is assumed to be the shortest path. A node marked as visited after relaxing all neighbors will not be revisited. So let's look at this diagram. What do you think is the shortest distance from A to B? Dijkstra only sees the path A to B and A to C, and greedily chooses A to B as 3 is less than 6. However, the true shortest path is A to C to B, as A to C is 6, and C to B is a negative weight of -4, and brings down the overall cost of the path. You might think, why not simply add a constant of 4 to all edges, so that all edges become non-negative? Let's look at this example. A to C to B is currently the shortest path. This has to stay the same. However, after adding a constant of 4 to all edges, A to C to B now has a weight of 10. However, A to B has a weight of 7. So now, A to B is shorter than A to C to B. This is because longer paths are disproportionately penalized when adding a constant to all edges. And since A to C to B is no longer the shortest path, it is theoretically incorrect, and hence, negative weights break Dijkstra's algorithm. Now let's move on to a deep dive of A-star search. It is an extension of Dijkstra, and is basically Dijkstra with an additional heuristic Hn. And the heuristic is the estimated cost to reach the goal. Dijkstra's priority function is Fn equals to Gn, where Gn is the total cost from the source to node n. However, A-star's priority function has an additional heuristic Hn. Let's look at how this plays out. A to B is 10, and A to C is 7. Dijkstra chooses A to C as 7 is less than 10. Now, for A-star search, we see that A to B is still 10, A to C is still 7. However, A-star search takes into account the additional heuristic, and the estimated cost from going to B to the end goal is 5. and the estimated cost from going to C to the end goal is 10. Dijkstra takes this into consideration and adds this heuristic to the current distance. This means that although a path is shorter right now, it does not mean it's a better path, as the estimated cost of reaching the goal might be higher. The quality and validity of A-star search is highly dependent on the heuristic.
Professors, my name is Jin Young, and I'll be going through the heuristic concepts and how heuristic affects A-star performance. For A-star to guarantee the shortest path, the heuristic must satisfy two properties. First, admissibility. For heuristic Hn, the estimate cost to reach the goal must never overestimates the true cost. Formally, Hn must be between 0 and H-star of n. Second, consistency. As you move closer to the goal, your heuristic estimates must not suddenly increase. Think of it like a GPS. It will not make sense if your estimated arrival time went up every time you drove closer. An admissible heuristic is only useful if it's also consistent. When both are satisfied, A-star is guaranteed to find the absolute shortest path. The quality of a heuristic Hn directly determines how efficient A-star is. In a fourth-direction grid, we use Manhattan distance as our heuristic, the total horizontal and vertical steps to the goal with no diagonals. If the heuristic Hn is 0, A-star has no direction and degrades to Dijkstra's algorithm. If the heuristic is low, A-star still finds the optimal path but wastes time on unnecessary loads. If the heuristic is perfect, A-star goes straight to the goal. If the heuristic is high but still missable, it's very efficient with very few nodes expansion. But if the heuristic overestimates, it breaks the algorithm entirely.
So for time complexity comparison, the prompt that we gave was to explain the best and worst case time complexities of A-star and Dijkstra's when using a Brownian heat implementation. So although both algorithms technically have the same worst case big O complexity, it should also tell us why purely judging A-star's efficiency of this is not accurate. For Dijkstra's algorithm, the best case is where it's a sparse graph, where E, the number of edges, equals to the number of vertices V, and it gives us OE log V. The worst case is when it's a dense and fully connected graph, which gives us OV plus E log V. For A-star, the best case is OD log D. It occurs when Hn equals to the true cost to the goal. The worst case is the same as Dijkstra's, which is OV plus E log V. It occurs when Hn equals 0, basically when A-star becomes Dijkstra's. It's important to note that the time complexity shown may vary depending on whether the complexity is derived from the number of nodes visited or by quantifying priority queue operations.
Thank you, Ben. Let's look at when to use Dijkstra versus A-star. The main advantage of A-star is efficiency, because it uses a heuristic to guide the search towards a single specific goal. It can terminate early the moment the target is found. However, Dijkstra is still highly relevant. We use it when we don't have a specific target or when there is no reliable heuristic to use. It's also actually faster for small, dense graph because calculating A-star's heuristic at every step takes more overhead time than Dijkstra's simple outward exploration. Moving to real-world applications, let's start with Dijkstra. It is the backbone of OSPF, a routing protocol used across the internet. A router needs the shortest path to all other routers in a network. Dijkstra is perfect here because it naturally calculates the shortest path to all vertices simultaneously. For A-star, the classic example is video game NPC pathfinding. An enemy character needs to navigate around obstacles to reach the player. A-star's heuristic efficiently guides the character straight to that single destination. Both algorithms remain essential tools today.
Now let's move on to the demonstration of our maze application. Our algorithm comparison function allows us to compare both Dijkstra's and A-star's algorithm against each other. We can adjust the speed of the demonstration. We can also expose the individual weight of each node. Here we can see that the A-star algorithm won, with fewer steps taken to complete the task. This is expected as A-star algorithm uses heuristics to guide its search, leading to fewer node expansions and a more directed search towards the goal. We also have our player versus algorithm feature, which allows us to choose an easy and hard mode, easy being Dijkstra's algorithm and hard being A-star algorithm. Here we compete against the algorithm to find the shortest path to the goal. There is also a show weights option for this game. Now let's speed up the gameplay. As you can see, we have won the game and this is the end of our presentation. Thank you.